Hi guys, welcome to the video tutorial for the Doppler effect, chapter 9.5. This will be part 1 of our 2-lesson series on chapter 9.5. So let's get right into this. So we're going to combine the first two learning objectives together because they're all kind of shown quite clearly in the diagram below. So the first thing to do is to sketch and interpret diagrams showing the shape of wavefronts as a source moves. So here we have two different diagrams. On the left, we have a stationary sound source. So everything we're going to be talking about today about the Doppler effect is going to only reference sound waves. Next time, we'll be looking at how light waves can also undergo a Doppler shift as well. But that's just a quick little bit more background information that this can extend to other types of waves as well. Okay, so in the stationary source, nothing too difficult or different from what we've seen before. If a sound source is emitting waves, then those waves are going to be consistent between two different observers at different points around the source. Now, on the right is where things get more interesting because this is what's happening now is what's known as a Doppler shift or the Doppler effect. And so observer B is going to observe or hear a sound that is going to be higher in frequency compared to that of observer A. So higher frequency, this person is going to hear a lower frequency. Whoops, not higher, lower. Now, if we were to have some numbers just so you can get a little gauge of what's going on here, observers A and B here would hear the same sounds. So let's say that's 330 hertz. And so A in the shifted Doppler case, so this is a shift away, will hear a lower frequency sound, so maybe 300 hertz, whereas B might hear a higher frequency sound, let's say 360 hertz. Okay, so that covers both of our learning objectives, that you're able to interpret wavefronts for somebody who's observing a source moving towards them, that's B. So those wavelengths will get shorter as the frequency increases. And then conversely, on the other side, the wavelengths will increase as the frequency decreases. So this should be pretty obvious if you think about our fundamental formula there from chapter 4, C equals to F lambda. So if the speed of sound, which is the speed of sound in the medium, in air, so speed of sound stays the same, sound, so that stays the same. And so, of course, if we increase one, we have to decrease the other. Likewise, if we decrease the other one also has to increase. Okay, so that should be pretty straightforward. Okay, next up are objectives, learning objectives 3 and 4. Use two equations commonly used to calculate the frequency heard as a result of the Doppler effect, and pay attention to plus and minus signs. So you'll recall from chapter 4 that I just wrote this formula down, V equals to F lambda. We can, of course, rearrange that as lambda equals to V over F. So what we're trying to say this time is we're studying a little bit of how the formulas are being derived. And so if the source isn't moving, then the wavelengths are going to stay the same. Okay, so same wavelength, 5 centimeter, 5 centimeter. Now, as it shifts, this is where things get a little bit interesting. And so what's going on here is we've got, we can say, we know that the wavelength for the orange segment is equal to the sum of the blue segment and the green segment. So that's highlighting this portion right here. So hopefully that's pretty obvious. The orange part is the longest, it's the whole thing, and then it's the addition of the two little parts together. Now, I suppose I probably should have done this if I was really referring to the line segments. This would be by is equal to ay minus by, and then substitute the values of the wavelengths. So normally speaking, we don't use different colors to represent all the different wavelengths, but that just helps you identify them. So we would have to use different abbreviations for that. And so what we're doing now is we're just resubstituting the wavelengths as this portion, V over F. So orange is the orange version, the blue is the blue version. Now, the interesting thing about the blue version here is this speed is the speed of the observer. Sorry, not the speed of the observer, the speed of the source. So it's how fast the ambulance might be moving. Whereas V is the speed of sound in the air. So naturally, if there's nothing happening, it would just be the speed of sound in the air. And so what we need to do is we need to subtract the two from each other, as we saw from our wavelength differences already, and then a little bit more algebra, and we get this particular formula here. So this formula is when the source moves to observer. And the formula down here is actually the exact opposite. This formula down here is the source moving away from observer. So it's just a difference in the plus sign, but as you can also tell over here, you can study this diagram over here, is the red wavelength is equal to AX plus AB, and a few more substitutions, and then you end up with adding the two together. We can see that you have to add AX to AB, okay, and as a result of that, by replacing them back with the from the wavelengths to the other version of the wavelength, right, V over F, then we have an addition instead. So altogether, you need to be familiar with this. So the equation gives it to you as both plus or minus. So it's up to you. Remember that minus is moving to observer, and plus is moving away from observer. Okay, so make sure you make a note of that in your data booklet. Next up, we're going to derive our second equation. And so our second equation comes from the idea that because the velocity is the same, we essentially have two different formulas. We have velocity, and I like to use before and after. So because the speed of sound doesn't change, right? We have essentially two different formulas like this. So this version, they use prime for after, but that's the way mathematicians like to write their things. Okay, so this is the velocity of the formula afterwards is equal to the frequency and the lambda, so the changed frequency and wavelength. And what we're doing here is we're combining our previous equation one together with this. Okay, so really what I'm going to do is I'm actually just going to put these two guys together. So I'm going to just do a lazy copy and paste. And then what we're doing is we're taking this piece and we're going to replace it, right? This is equal to lambda. And so what I'm going to do is I'm just going to erase this and I'm going to attach this directly beside it. Like that. Okay, so this is our second formula. Actually no, they usually like to write this as, they like to have this on the other side by itself. So what I'm going to do is I'm going to do the algebra. So I'm just going to go through the algebra for that. So I'm going to leave f prime on this side. So that's going to be v times f, v plus or minus us. So the speed of the observer. And then so I'm just going to throw that back over here. Oops. Let's try that again. Throw this over here. Okay, and then you can just move this, right? So that's just rearranging it back. Right, so that's the algebra for the second equation. Okay, and plus or minus, again, remember minus moving to, plus moving away. Okay, so what we looked at so far was that the ambulance is moving to the observer. But what can happen now is that the observer can move closer and closer and closer to the ambulance. And opposite to that, the observer can also move away from the ambulance, way, way, way far away. Okay? So now we're going to start looking at, rather than the source moving, what happens when the observer moves. Okay? So the Doppler shift still happens, but there's just a slight little change in the formulas. Okay? So let's get right into this. So before, velocity before equals to frequency before multiplied by the wavelength before. The observer isn't moving. Afterwards, so I use the color blue to help separate the two different pieces of information. So afterwards, we know that the wavelength doesn't change. Okay, this wavelength will always remain the same, right? Because the source isn't actually moving. The wavelength will stay constant. But what happens is as the observer moves into it, it's speeding up the waves. Okay, and so as a result of that, the wave velocity is going to change. And so the velocity of the wave afterwards is the addition of the original speed of the wave, that's essentially the speed of sound in the air, at whatever temperature it happened to have been, plus the speed of the observer. Okay, speed of the observer plus the speed of sound in the air. And so I've just made a quick note of that right here. So I don't really need an arrow for that. And so what we're going to do is we will do some rearrangement of this now that we've explained both of these situations. We will look at a formula derivation. But first off, let's just think very quickly. We know the velocity is increasing. We already saw that connection over here. We know that the wavelength is going to be constant. So what has to happen to the frequency given that lambda stays constant and VA is increasing? Okay, so take a moment, take a guess, make your prediction. Is the frequency going to increase? Is it going to decrease? Or is it going to stay constant? So hopefully your prediction was that the frequency was going up, or is that it was going to increase? Because we need to keep both sides of the formula balanced. Lambda is not changing. V goes up. Therefore, frequency also has to go up to keep this balanced. Otherwise, you'll have it'll be unbalanced. Okay, and so what we're going to do is we're going to combine. We're actually going to combine three different formulas together to form our new piece here. So we're going to take three things to form this guy. And actually the missing piece, I forgot to write it down. The missing piece is that the velocity after is the original speed plus the speed of the observer. So this formula, or this little thing, we already mentioned. Where was that? Right here. Right here. Okay, so really, it's that, and we're combining three different things together. And so what's going on here is, let me just maybe repeat this one more time with you guys. So I'm just going to move this over here to the side. So this is what's really happening. And so what happened was we started with this. We then replaced VA. Whoops. No thanks. We replaced VA. Oh, stop doing that, please. Let's try going the other way. Okay, maybe I'm not going fast enough. No, it doesn't like that. Okay. All right, I'm just gonna have to rewrite it then. So VA is VB plus UO. Lambda is a rearrangement of what is over here. So that was VB over FB. Okay, and so that's why we have this particular version right here. Okay, so if we further simplified that a little bit, whoops. So if we further simplified that a little bit, I'm just going to move this back. So that's how we got this, was a combination of those three formulas. A little bit of simplification and separation, and you can have two different forms. You can have this form or this form. They're both equivalent of each other. I think this is the one that data booklet uses. Okay, but it's just simple algebra. You can rearrange it yourself as you like. And this is the equation for when the observer is moving towards a source. And so if you're thinking, wait a minute, before there was a plus and a minus, so it probably turns out that with a minus, then it would mean that the observer is moving away from the source. So this portion down here is observer is moving away from the source. Okay, so this time it's a little bit differently. So plus is moving towards, minus is moving away. Okay, and if we compare that from before, plus is moving away, minus is moving to. Here, plus is moving towards and minus is moving away. So the two formulas kind of flip because the situation itself has also reversed as well. So the best thing to do is just remember one, and you know that as it flips, that's why the plus and minus also flips in terms of moving away, moving towards as well. Okay, so let's have a look at a few examples here. So here we have an ambulance emitting a sound of 320 hertz. So that's going to be frequency. Observer hears a sound, so that's F prime. And the speed of sound is that, 340 meters per second. And we're asked to find how fast the ambulance is moving. So that is U of the source, the velocity of the source. And so this is our first example here. So we are looking at equation number 2, number 1. Let's see, what we're trying to find again? How fast is the ambulance moving? Okay. How fast? So we need V prime, don't we? Oh no, we need US. Okay. So either one can do it. I'm going to grab this one, equation number 1. Okay, I'm going to paste that down. And let's make our substitutions. So no, actually we got frequency. We have quite a bit of frequency information. So we don't want to use equation number 1. We actually want to use equation number 2. Okay, so we have frequency before and after. Oops. Okay, so frequency before, I'm just going to replace it. Frequency before is 340 hertz. Frequency, there's frequency after. Frequency before was 320. Oops. So that's 320. And then this is the velocity and speed of sound in the air, so that's 340. So I'm just going to take that, I'm going to copy and paste it. Oh, okay. So 340 meters per second. Just going to duplicate that. And so that's multiplying. And in this case, it's moving towards the observer, and that should be a subtraction, moving towards, right? Let me just double check that. I'm getting lazy now. Moving to, yep, subtraction. Okay, so once we crunch this down, so this is straight from Cognity, and we should get 20 meters per second. So US will get 20 meters per second after we do all the substitutions. Okay, continue on with example number 2. A source emits a sound of frequency 2 hertz, 200 hertz. And the speed of air is 330 meters per second. So that's 200 hertz. Speed of sound, 330. Calculate the frequency measured by an observer if the observer is moving towards. Okay, that's interesting. Frequency of the observer is moving towards. That's US, 130 meters per second. So this is our second set of formulas here. And so I'm going to use this version. Moving towards is plus. Sorry, I'm going to place that as. So moving towards is a plus, so I'm just going to erase the negative. Okay, so before and after, let's see here. Calculate the frequency measured by the observer. So that's going to be afterwards. So that's actually the way that this formula is. I like to use before and after, but you get the booklet gives it as F and F prime. So the frequency observed afterwards is the frequency before, 200 hertz, 1 plus the observer moving, sorry, not the source moving, that's the observer moving this time, 130 meters per second, and the velocity before was that, 330 meters per second. And so if we rounded that off, that's going to give us 280 hertz. I think it's actually about 278. I just rounded that up, 280 hertz. Okay, lastly, we have a sonar as a common way of detecting objects underwater. The sonar emits a wave that reflects objects. Stationary object emits a sound of 800 hertz, sorry, 8,400 hertz towards an object moving towards a submarine. Sounds reflected by an object. Actually, this reflection thing, let's look at this another time, okay? So we'll cover this next lesson, all right? Okay, that's it for the Doppler effect for today. Next time, we'll look at Doppler effect looking at light shifts. See you guys then. Bye-bye.